So Q ADT. ADT means when we combine the data in all related operations, that is said to be abstract data type ADT. So data can be held in any of the data structure. So if we hold data in Q, that makes it QADT. So ADT is the data and all related operations on it. So how do we actually handle the data depends on what type of data structure we are using. That is QADT. So this particular data structure may take a few shapes, I mean, few forms of understanding, as in sometimes people just don't consider anything about what will happen when the queue will be full, as in both as this queue has got two pointers and they both go forward. When we add, it goes forward. When we delete, it goes forward. So what happens to all of those left spaces in the back? Sometimes we do care about it, sometimes we don't. So if we don't, nobody cares. But if we do, then we have got two ways dealing with it, either circular queues or adjusting queues. In circular queues, what actually happens then when both of the pointers reach at the end of the array to get back in the back. All right, so it doesn't matter if the queue is getting emptied in the back, as when the pointer reaches to the upper bound of the array, it gets back to the start of the array. This is called circular queue, and both the pointers run after each other and then in circles. Second one is adjusting. In adjusting, what basically happens when we add the data, the rear pointer does go forward, but when we delete the data, we don't have a pointer at the front. Rather, what basically happens, we pick the data from the front and bring the whole queue to one point to the left. What does it mean? We pick the first value from the queue and then we move all onwards item one position back. So that is adjusting queue. So we are always picking up the data from the first position, and when this data is picked up, deleted, all further positions will be pushed back. So this is adjusting queue. All right. So this is about circular queue, this particular lecture. So let's start with the introduction of the queue. Queue is a data structure which has the rule of first in, first out. What does it mean? It means that what enters the queue first will get out first. So as you can see that the data is coming out from the front. It's like you are in a queue. So if you are first, you will be handled first. If you are in the back, you will be handled at the end. As the car goes forward, it points towards the front. All right. Let's say that if the car is going through a tunnel, when it will come out, it will come out from the front of the tunnel. So it is entering from the rear of the tunnel and coming out from the front of the tunnel. That is why the front pointer will be used to delete the data and rear pointer will be used to insert the data. So let's say we have got this array of four positions starting from 0, index, then 1, then 2, then 3. There are four elements in the array. As I just described, that from the front we will delete and from the rear we will insert. So let's say that deleting a queue is called DQ. We will use the same subroutine name DQ, and we are using insert for NQ. All right. We are using the word NQ for the word insert, and we are using the word DQ, and we will be using for delete, and we will be using same subroutine name. So let's say we have got this array over here from 0 to 5, 6 total locations. Front pointer is 27 and rear pointer is at the front pointer it is 27 at position 0, and it is 20 at the rear pointer at index 3. As I just told you that we add at the rear, so it means that when we add the data, rear pointer will go forward, and when we delete the data, we will be deleting the data from the position at the front pointer, from the index at the front pointer. And let's say we DQ. Once we DQ, this front pointer will actually comes forward. When we delete, this front pointer comes forward. When we add, this rear pointer comes forward. In any of the cases, they both are being added. So let's say we DQ'd and then 27 will be removed. You need to understand one thing, that when the data is removed does not mean it is cleaned up from the array. All it means that the front pointer is now has moved forward. 27 is there. In the code, what we will do, we will assign none to it so that it could be noticeable that this 27 is now removed. Let's say afterwards we enqueued, we inserted two more values, 31 and 55. In that case, the rear pointer will be now at 5. So what is the operation? Add 1 to rear pointer and add the rear pointer at the new value, that's 31. And then add another 1 to rear pointer, move it forward to 5, and then add 55 to it. So now you can see that two values, 31 and 55 are added to the Q array. Now, if we DQ, rear front pointer was at 34, now it has moved forward and we DQ 34 for it. Okay, so that is how this operation goes further. And then you can see over here that rear pointer is already at the upper bound of the array. Okay, so but we have got these two places now emptied, as these two have already been read and deleted. So we can add further two values. For that, we would have to move this pointer back to 0 to add a new value. So we enqueued, or we have added 75, and this rear pointer has now gone back to position 0. So front pointer apparently over here, as from the point of view of index, is ahead of front pointer, but logically it is basically following rear pointer. Okay, so now the next value that will be DQ'd will be 93, and rear will be at 0, and we can add one more space to it. Okay, so in this case we would have two more variables. One would be queue pull. Queue pull will be basically the number of items in the queue, and uh, we would have queue pull variable that will be telling, and queue size, queue length, at how many items that we have added to the queue. In this particular case, we have got 93, 20, 31, 55, 4 item, and this is the fifth item, but the length of the array is basically 6, so we can add at most 6 items to the queue. All right, so we would have queue full, which means that how many items that we can add to this array for the queue. And what is the size of the queue? Size of the queue is not associated with the array length. Array length is the maximum number of positions, the maximum number of item that we can add to this queue, because we cannot go beyond the array size, because we are implementing this queue using an array. So length of the queue is a count, starts from the front pointer and ends at the rear pointer. So 1, 2, 3, 4, 5. It is not the length of the array by which the queue is limited. So the size of the queue cannot go beyond the length of the array, but if the array has got 6 positions and there is only one item in the queue, the length of the queue would be 1. All right. So that is how we perceive this queue ADT. Now let's see the pseudocode. So first, we will be setting up a queue. So let's declare a queue from 0 to 9. So for our case, this would be 0 to 5. We had how many? 1, 2, 3, 4, 5, 6. Yes, 0 to 5. And then we declare upper bound, rear pointer, front pointer, queue full, queue length. Rear pointer will be the pointer from where we will be adding data. We will be adding data to the queue. Front pointer is the location from where we will be deleting the data from the queue. Queue full is basically the maximum number of elements that we can add to the queue. This would be limited by the number of elements in the array. This would be 6 then. And then queue length. What is the current length of the queue? Means how many items there are in the queue, so that we could use these two to determine the amount of items that can still be added to the queue, or they are already being added to the queue. So front pointer is basically 0. Remember, from the front pointer we will add the data. Sorry, we will delete the data, and rear pointer is what we are making -1 for the reason that we add 1 to the rear pointer and then we add it. Okay. And then upper bound is now 4, because we are starting from 0 and we are going up to, oh, this would be uh, uh, 0, 1, 2, 3, 4, 5. So 0 to 5. Upper bound would be um, 5 then. Let's make it 0 to 0, 1, 2, 3, 4, 5. Okay. So upper bound will be 5. Q will be full. Actually, I planned it for 4. Let's plan it for 4. So array would be from 0 to 4. Upper bound will be then 4. And Q will be full when there are 5 elements, means 0 to 4, that becomes 5. And the length of the queue, currently the length of the queue is 0. And then we move none to queue. Now, this is another thing that you have to keep in your mind when we are using array as a data structure. And the size of the data structure is determined. The size of the data structure is determined. In that case, you would have to actually show all the positions. So in that case, we will be filling the whole queue array with basically none. None is none value. It is just something. Since if you won't put none to it and you try to print the queue, you would see nothing there or as many items which are actually not as the total amount of element that you can add to the queue. Means if there are two items in the queue, it will only show two. So this is not required. User must see that how many positions do we have in the array and what are the values that are entered in the queue. So the idea is when the queue will be empty, all the elements would be seen as none, 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 none. And if there are a couple of elements, then those two elements will be shown and rest of the elements will be shown as none. So that is the initialization of the queue. That is the initialization of the pointer. These are the constant values, tuple and upper bound. These are constant values. And then this is the current queue length, which is 0 now. Now, insert an item, which I just said in queue. It receives the array and the item that needs to be added to this particular array. Okay, so if queue length is less than queue full, it means what? The current length of the queue is not has reached to the total number of items that we can enter to the queue. If it is less than that, then we will see that if the rear pointer from where we have to enter the data, it is less than upper bound, then we will increase the rear pointer. And initially rear pointer was -1, so it will become 0. So means that we are now going to add the first item at 0. So if it has already reached, it is not less than upper bound, rather it is equal to upper bound, then the circular operation will happen and the pointer will go back at the start of the queue. Now the queue length will be increased as we are basically adding an item. Now you need to remember that these four values, front pointer, rear pointer, upper bound, queue full, and queue length are in global space. They will be global variable so that they are made available to both of the subroutines. So this subroutine procedure is basically accepting an item, setting the rear pointer as we are adding the items always at the rear pointer, increasing the length of the queue, and then adding the item at the current rear pointer position. Remember, we add to the rear pointer, and if rear pointer is at the upper bound, it will move back to 0. And then if queue length is has reached already to the maximum available elements in the queue array, then it means that the item that is received cannot be added any further. So this is called overflow when we don't have space in the queue and still we are trying to add to it. So this error will be output rather than anything else happen. Okay, so this is the end of the procedure. Which procedure? Enqueue. Now deleting an item, which is dequeue. Function dequeue accepts an array from which it will dequeue or basically delete one of the item. And since we are adding numbers to it, so it will return the item that is actually deleted. So this is a function because it is returning a value. Since it is returning a value, so it is said to be a function. If queue length is equal to 0, obviously if all the elements in the queue are already deleted, current length is zero. For example, right at the start of the program, if we try to dequeue, it will say this is basically underflow. Underflow is an error that appears when there are no items and we are trying to delete them. So if queue length is equal to zero, then it returns. This is a function, so it will return minus one. Minus one when it reaches to the caller calling subroutine. That subroutine will have an idea that there are no items in the queue to dequeue. If it is not zero length, then it goes in and it picks up the element or the item which is at the front pointer and assigns it to item. And then we move none to that particular queue location for the reason that this item has already been read and we want to show it to the user that that item is now scratched. So we basically scratch the item and then we check if front pointer is equal to the upper bound, means front has already reached, because both the front and the rear pointer are moving forward with their respective operations. Even front pointer, if it has already moved at upper bound and we move it forward, there is no further space, but yet we can go back and make the circular uh, thing. And then front pointer, if it is equal to already to upper bound, we will make it zero. Otherwise, we will just increase front pointer to an other next position. So one. If it is three, it will become four. Now, after adjusting front pointer, we will decrease the length of the queue since we have dequeued. And then afterwards, at the end, if this return has not reached, we will return the item that is being retrieved or deleted from the queue. So that is how it works. Now let's see how to apply this algorithm to Python. As usual, we are using MU editor. So let's start with NQ. So define NQ, this is procedure. NQ, it receives the array and the item that needs to be added. And then we will be using out of these one, two, three, four, five variables in global space over here in this particular algorithm, we will be using Q length, Q full, rear pointer. So we would have to basically first tell in Python that what are these variables and if these are available in global space and we want to use the same. So these three variables we are making use of them are from the global scope. So these are global variable. So in pseudocode or in Visual Basic Code, when we declare a variable in the global space, it is readily available everywhere. But in Python, if you like to use a global variable, you would have to tell that separately in every subroutine that you want to use global variables. So this line is a must for all those variables which you are actually using in this subroutine from the global scope of this program. So if length q length is less than q full, you can eagerly compare this pseudocode with this Python code. Although I have changed the name of the variables, I have made them a bit little, but they are the same. So if query length is less than query full, and then we are checking if the rear pointer is less than upper bound, then we increase the pointer as we move the pointer back to the first position as it is happening over here. We are changing the length of the queue and we are reading the item into the new rear position queues element. Okay, so this is how we have actually received an item and added to the new position of the rear pointer after adjusting it one location forward. But if the queue length is basically, sir, upper bound B global, yes, upper bound B global, yes, upper bound is also global. So, but upper bound we are not using over here. Yes, we are using. So upper bound will also be global. Okay. Now, so upper bound is adjusted as global variable over here. Rear pointer is less than upper bound. Yes, it is all done now. And if it is Q length equal to Q full, in that case, we would have this overflow error, which means that Q is full and item cannot be added anymore. Okay, now DQ. In DQ, this is a function, so it is returning value as we have shown over here. This is DQ. Now, Q length, front pointer, and upper bound, these are global. If Q length is equal to 0, in that case, we return -1. If it is not, we are basically going into the procedure. We read the item from the current front pointer's value, and then we move none to that particular location as it has already been read in item, and then this item will be returned. If the front pointer is equal to upper bound, we will move it back to the start of the queue, and if it is not, then we will add one to the queue. In any of the cases, if we have read one item, we will decrease the queue length by 1. We will decrease the length of the queue by 1. So this queue length is basically in else, this else. Now, afterwards, we return the item, and that's the end of the function. Now, let's start the way we discussed in that particular board. Let's patch that board first. So basically, what is happening? First, we have 27. See, we set up from 0 to 5. 0 to 5 means it will actually work from 0 to 4. So this is actually from 0 to 4. In Python, the upper limit is not used. Rather, it is always upper limit -1. So this goes from 0 to 4. Front pointer will be 0, rear pointer will be -1, upper bound will be 4, Q full will be 5, Q length is equal to 0. So these global variables are all now set. This Q is basically the list or the array that we are going to use, and we are filling it with none, 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 none 5 times. at every position. So this particular syntax will fill none into the whole queue from 0 to fourth location. Now, as you can see that we have got 27, 34, 93 and 20. So we have added these 27, 34, 93 and 20 in same order. Let's run this program and see at first when we have moved none. Let's put one print over here as well. Let's execute this program. So at first you can see it is all 0, 1, 2, 3, 4. All values are basically none at the start. Okay. Then we add 27 to it. Over here, we called enqueue with 27. So we have added 27. Rest of the values are none. As you can see, no matter how many values are there, is still the whole array is being seen. This is what I wanted from this none thing. So 27 is added. Afterwards, we printed it and then we enqueued 34. 34 is added over here. So none got removed. And then we added 93. There we go, 93. Then we added 20. There we go, 20. So now the front pointer is at 0 as we initialize it at 0 and rear pointer is at basically 3. Now what will happen? We dequeue. We dequeue 27. As soon as we dequeued, we received 27 in X. You can see over here. So 27 is now removed. So this 27 is removed now. Now we enqueued 31 and 55. We enqueued 31. 27 is removed, none has replaced it. Okay, then we added what? 31 to it, 31 is there, and then we added 55. Since this is an array from 0 to 5, the array that we have over here is 0 to 4, this 55 is now added at the start. Now the position of rear pointer is 0 and the position of front pointer is 34. And then afterwards, we tried adding 65, sorry, 55 that is added, and then we tried adding 65 that it says overflow error, queue is full, item cannot be added. As you can see that rear pointer is actually at 34 and front pointer is now at sorry, front pointer is at 34 and rear pointer is now 55. So we cannot add the 65 over here. So this is overflow. Afterwards, we dequeued one more. So this 34 is removed now. This 34 is removed now. So it has been replaced with none. Now this one space is available. So we can add one more item to it. So we added what? 75 and 75 has replaced it. So rear pointer is at this one and front pointer is at this 0, 1, 2. So the whole code works very well. There is no discrepancy to it. So I basically invite you to write that adjusting queue thing by yourself so that you have a good idea of these queue data structures, ADT. So that's about it for